Yeah, thank you very much, Duncan. Thank you very much for the invitation and for having me here and giving me the opportunity to talk about my experience and some of the work that we have done here in Siemens Technology. I will mostly talk today about a project, a US Department of Energy RPE funded project that we have together with Hawaii and some other partners that you can see here, PNNL, I'm sure there will be people here in the call, Opel RT, our business unit, Siemens Digital Grid. So there's a long list of people contributing to this work. Of course, it's not only my own work. And the purpose is to demonstrate how we can achieve N-1 secure operation of an island system that is 100% inverter-based in a real operational setting. And we call this dynamic security optimization. And throughout the presentation, you will see what dynamic security optimization means and how it helps us to optimize and operate power systems with high grid-forming inverter-based resources contribution. Before going to the technical part, and now let me see if this works. PowerPoint was playing me some tricks today. Before going to the technical part, I want to give you a little bit of my personal background. As Duncan already mentioned, I'm a principal key expert for control systems as well as head of autonomous systems and control in our research center here in Siemens Technology in Princeton. And I have three main technical backgrounds that topics I worked on through my career. I did my PhD in automatic control. Just today found out, had a meeting with another colleague who studied at the same university. Some of you may know that there is a strong control group in Stuttgart, even though the university itself may not be so famous. And that was focused on robust and distributed control, which if you work with grid-forming inverters, inverter-dominated systems, is the, let's say, control theory behind understanding stabilization of power systems. When I finished my PhD, I first worked for another company developing solar inverters. I was control system architect there and responsible for those areas was residential solar inverters. And then about 10 years ago, I moved to Siemens, as Duncan said, first 5 years in Munich in our research center in Germany. And now since 5 years, I'm here in the US in Princeton. And over those 10 years in different roles, always working around grid forming inverters, how to bring them in, for example, Siemens' first hybrid power plant that consists of diesel generators, batteries, and the solar plant. This is running on Galapagos Islands now since 3 years, and always centered around grid forming and how to operate larger transmission systems with grid forming inverters. Maybe also as a side remark, Siemens is selling grid forming inverters since more than 10 years, mostly for special systems, for example, container ships and other applications, offshore platforms. Now, looking into the technical problem that we are talking about today, and I'm sure many of you are very well familiar, probably all of you are very well familiar with the challenges that we see when we have high renewable integration. I'm just listing here, from my perspective, there are 3 different areas where we have to address. One, of course, is power balance. Renewable generation is not necessarily matching what you need for the load, but wind is blowing when the wind is blowing and the sun is shining when you have sun during the day. The famous duck curve, of course, from California is all over the place and has been predicted maybe 8 or 10 years ago. And today we are seeing that exactly these things are happening. Another big challenge that we face as we have more and more renewable integrations, of course, power transfer, because your generation and your loads may not be in the same location. So you need more transmission capabilities, or you need a smarter way how to orchestrate generation and load locally and not over larger areas. And last but not least, you need power system stability, which has 2 main components, which is N-1 security and protection schemes. And this is the topic we will be mostly talking about today in my presentation and discussion. Now, from a technical point of view, what is interesting is that for the first 2, we have technical solutions today. You can use batteries, you can use different kinds of power flow optimization algorithms. I'm not saying those problems are solved. By far, they are not. Batteries are still expensive, and there are challenges that we face if we would say we want to turn our systems in 1 or 2 years into 100% renewables. But technically, we know how we can do it. Now, for power system stability, and of course, that's also the reason why this uniform consortium was built by DOE, is that actually from my perspective, we don't even know how to do it. We have ideas of grid forming inverters. We have ideas how they can play together. But if you really think of a really large system, like, for example, the Eastern interconnection or the Western interconnection, it will be very difficult from the knowledge that we have today to really say, okay, this is exactly the path forward. And as I said, that's the reason why the Unified Consortium was set up. And the work that we are doing shall shed some light how something like this can work. Sure. Now, obviously, again, I'm telling you things that you know already. This is a highly important topic that many transmission system operators around the globe are facing. I'm just listing here a few that have very high integration of inverter-based resources. You see here the term at the bottom left, system non-synchronous penetration, which is a term that I will use here, taken from the IOGrid reports describing the instantaneous power generated from wind and solar divided by the load of the system. And you can see here a couple of countries or islands, large islands, that are already at very high percentages, around 60%, and target 100% within the next 3 to 10 years. And this requires, of course, even if it's not around the year, just for a few hours you want to operate a system, it requires already today that we have technologies for which, as I just said earlier, we don't actually even know how it works beyond, I would say, small microgrids. And that this has an impact today is also something I would like to illustrate with this slide. You see here data from Ireland from 2020, so almost 2 years old. At the bottom figure, you see February 15th, 2020. You can see the red curve, which is the demand on that day, and the green curve is the wind generation. And you can see here that in the morning hours, as the demand goes down, also the wind generation is curtailed. Yeah. Obviously, something we don't want to do, but we have to do it because in Ireland, they are requiring to have a certain number of synchronous machines running at any time. So there is no way actually to keep the wind flat, even though there is wind blowing, they have to curtail it. And obviously that's something we would like to overcome. And what is even more pressing, I think, for this problem is, if you look at this is just one day, but if you look at the whole month of February, you can see that almost every night we see this dip, which means every night wind generation is curtailed. Now imagine they install another few hundred megawatt of wind generation in the month of February 2020, they wouldn't have produced much more renewable energy in the system. So it is a problem which TSOs are, of course, already facing today, not everywhere, but in some large islands that have high inverter-based resource integration. So I will take you in this talk through a few topics. First, I will talk a little bit about N-1 security in low inertia systems, what it means and what are the different challenges that come together. I will talk about our experience here at Siemens, different projects I was also personally involved. And then the last two parts will be talking about our solution we're developing together with HECO, and finally showing some results. So what is the problem of N-1 security in low inertia systems? And I've shown this here as multiple layers from the bottom, grid forming inverters. Of course, that's everybody's talking about. How can we make inverters grid forming? There are different concepts flowing around. I'm not going to repeat this here, but it's just a very basic layer to understand N-1 security. The next layer is intergenerator oscillations. Again, a topic that I'm sure most of you, if not all of you, are familiar. If you plug in multiple grid forming and grid following inverters, you tend to see oscillations between the generators, something we need to address. And also one issue that we will see, and of course is also reflected in the Unify consortium as it's set up, is that in the past, large transmission systems, we simulated it in RMS simulations. Now we have to potentially go to EMT simulations to have the level of accuracy that we need in low inertia power systems. Now, one layer on top, which is even more complicated, is this today's power systems. They are stabilized, for example, with power system stabilizers and other measures, but it works nicely because the eigenmodes of the system, so how your system is actually oscillating, the generators are oscillating against each other, is time invariant. If you look at large transmission systems, the eigenmodes like east against west or north against south are not changing over time. And the main reason is that these eigenmodes are dominated by these large power plants, large synchronous machines, and they are not changing over time. These machines are running 24/7. Now, if you start replacing those machines with wind farms, maybe large batteries or large solar power plants, we will have time varying eigenmodes, because at some times there will be no wind and no sun. So you have a synchronous machine dominated system. At some times it may be zero inertia. And of course, there may be any percentage in between. So you're actually changing between systems that have zero inertia, zero systems that had a lot of inertia, and systems that have maybe more inertia in some areas and less inertia in other areas. And that brings a fundamentally new challenge into the picture, because today stability analysis is analyzed by simulations, can take weeks or months to study. Then you parameterize your system and you know it's running like this for the next years until large change in the generation. Now, as these things are going to change, not within minutes, but within hours, days, and weeks, we need something which is guaranteeing the N-1 security on the fly as the system is running. And that's what we call dynamic security optimization. N-1 security, I'm sure everybody is familiar, means that the system can withstand any single outage, single component outage, power plant, power line, for example, without having a larger blackout in the system. And this is something we need to do online in order to make sure the lights stay on and we don't have a big blackout. Now, what is the expertise, or what have we done? As I mentioned, I'm working on this since many years. You see on the left-hand side, again, the different layers and challenges that we have to address. My thought or my philosophy behind the different projects that I'm working on and that my team is working on is that we have to start with smaller systems, learn in smaller island systems, but at the same time also build scalable solutions that can scale to large and really large transmission systems. And that's what you see here in the picture on the right. A few projects I was involved in. We did a field test in 2017 in Bavaria in Germany, where we had a small part of a village, part of a feeder disconnected from the main grid, running in an islanded system and supplied with 6 parallel grid forming inverters. This is our office building, which we converted into a microgrid, and we can run it also as an islanded system for testing purposes. I mentioned already the Galapagos project, which is running now since 2018 reliably, and it's able to operate without any inertia, at least when there's not enough solar generation. Siemens is building a new power plant in Guantanamo Bay. Similar setup. There are times and scenarios where the system is supposed to operate only with zero inertia, and of course we have to make sure the lights never go out on a naval basis. These are the 2 DOE-funded projects I'm currently leading, one together with NREL and the Holy Cross Energy from the Rocky Mountains, and the second one then with Hawaii I will be talking about today. The Dynagrid Control Center was a project we had in Germany, also looking at larger systems and how we can operate them. What you see here on the right-hand side is all of them address grid forming inverters, all of them address combination and parallel grid forming from multiple grid forming inverters. Hawaii is the only one which really covers the complete scale up to guaranteeing N-1 security in the setup. So let me now dive a little bit deeper into what we are doing in this project. The purpose of the project is to demonstrate dynamic security optimization. That means that we can operate a system with zero inertia. Now the lights go off here. With zero inertia and run through different contingencies. What we developed for this is a system, we call it an operator support system. You can think of it as an assistance system like you have it in your car, which dynamically adjusts the parameters of your system to make sure you're always N-1 secure. As I said earlier, the eigenmodes of your system are changing, not within minutes, but within hours, days, or weeks. So you continuously adapt your system to make sure it's N-1 secure. And that way we can also scale it to large systems where the eigenmodes are changing and may not be repeating for a longer time. And we are demonstrating this, and I think that's also quite unique of this project, not just in papers and offline simulations, but we're actually building a demonstrator how this system could look like, consisting of a real-time simulation of the island from Hawaii. And thanks here from Opal RT, maybe you guys are also here in the meeting today. for the support here. We have a commercial energy management system from Siemens, Spectrum Power 7, which is controlling the system. And then we have dynamic security assessment, another product from Siemens, which is doing the analysis of the dynamic security, and then the optimization here on top, which is optimizing the parameters. And I will go into detail in the next. Of course, I also would like to thank DOE for the support here of this project and all the other partners, PNNL and Hawaiian Electric. Now, looking a little bit deeper into this operator support system, what is it doing? So you have your power system, you gather measurements from the system, usually standard RTU measurements, you get a state estimate, so you know where is your system now. And then you run an analysis, which is comparing different critical contingencies that you identify beforehand, and you're running fast simulations in order to analyze, is your system oscillating, are contingencies critical, or are they not? If you identify their critical contingencies, you're running an optimization, which I explain on the next slide, in order to tune the parameters of your system to make your system more stable. And then we have a verification phase, again, running simulations, nonlinear simulations to verify the parameters are actually showing the improvements we expect. And then you send these controller parameters down to the system and implement it on the field. This loop that you see here is running whenever there's a need, maybe every 15 minutes, maybe whenever there's a major change in your generation mix or in your dispatch. Or maybe when the load is changing. So it's not a real-time control loop. It can run slowly. Once we have optimized the controller parameters and sent them to the system is N-1 secure and does not require real-time communication or any real-time interaction from the control center. That's from our perspective very important, because utilities usually don't want to rely on basically adjusting your system or stabilizing your system during these contingencies. We have options to include remote measurements, for example, inside this controller, but I'm focusing here only on controllers using only local measurements. So is this controller tuning working? And that's just really in a very brief summary on one slide. So we start with the nonlinear model that you use for simulations. It could be an RMS model. We are also working on extensions with ENT models. And then if you have the system time domain behavior, as you see here on the left-hand side, and you transfer it in the frequency domain, these oscillations you see here correspond to a peak in the frequency domain. Now, in order to, and what we are doing in our optimization is we find the right, let's say, knobs that you have to tune in your system in order to bring this peak down. And once you have reduced this peak in the frequency domain, also your time domain looks much smoother. And you avoid usually overshoots and all the other pieces basically coming for free. This optimization works by linearizing this model. And then you see here, the key part is that we have parameters, and I will show this on the next slide, what these parameters are. We have controller parameters defined for each of the different generators, conventional, renewable, batteries, and other generators. And we put all these parameters in, let's say, optimization engine that finds the right set of parameters to bring down these peaks. The optimization we use here is called H-infinity optimization. I'm sure many of you have a strong controls background. H-infinity is a standard technique that has been used for many years. The challenge here was that first, usually you don't consider problem classes of this kind, where your matrices A, B, and C are depending on your controller parameters. And second, the systems that we are looking at can be very large. So you can have hundreds or even thousands of states and controller parameters. And finding optimization or an algorithm that solves this optimization in a reasonable time, I would say, was the biggest challenge along the way. Now, let's have a closer look at the models we are optimizing. I mentioned earlier, so these parameters K that we are actually tuning, what are the knobs that we can play with? This is just an example for a conventional power plant. So we have a synchronous generator, we have a voltage regulator and exciter, we have a power system stabilizer in this case, and we have a turbine and the governor. You see here just standard examples. This is not the models we use from Hawaii. Their models, as you can imagine, are confidential, so I cannot share them. These are just standard, some random models. You can find them in IEEE recommended practices. And then we discussed with different experts what are parameters that are, let's say, software parameters that we can tune and not physicals like the inertia of your turbine or something like this. And we identified them here, and you see them as red parameters, and these are the parameters that we are tuning. Of course, we can tune other parameters. This is just an exemplary selection of parameters. Now, this is a conventional plant looking at an grid forming inverter. This is the model for a grid forming inverter that we use in our system. It's a very, I would say, standard control structure for a grid forming inverter. We have here droops. We have low pass filters for both the frequency and the voltage. There is also a fairly simple voltage controller. We have a component for virtual inertia, which we are actually not using at this point. But we plan to use it at a later point in the project, or at least see if it has any advantages. And here we are tuning the time constants and the droop gains, the gains of your droop controllers. We have chosen this kind of a structure for multiple reasons. First, it's a structure that Siemens is using in one of its grid forming inverters, and it's publicly available. Probably many of you know, if you talk to manufacturers of grid forming inverters and you ask them about block diagrams, you know you don't get answers, or at least not the answers you're hoping for. I can tell you from the projects that we have been involved with real customers and real grid forming inverters, even for us, it's very difficult and sometimes impossible if it's a non-Siemens grid forming inverter to get anything close to a block diagram like this. But as I said, Siemens has one grid forming inverter where the control diagram, that the structure is open, and that this is this one, so it's resembling one for Siemens that we are also using in our commercial projects. We could replace it by a more complex one, just giving you here some thoughts on that. Now, how do we test the system now? As I said, we want to run through different scenarios, 100% inverter based, but also lower percentages. So what we took is today's studies, how HECO would run them in a grid extension study. So we first extended the island to actually get to 100%. I'm not going through the numbers in detail. Okay. Now my PowerPoint is playing me tricks. Okay, I hope can you see this again? Just want to be sure.
Yes, we can.
Okay, perfect. So we increased, we added, for example, as you can see here on the figure on the left, we added large utility scale battery and PV systems. When we started the project, the plan from Hawaii was to add 2 large utility scale hybrid plants, so PV plus battery. We said 2 is not enough, so we planned for 4. Today, the plan for Big Island is actually to add 5 instead of 4. So in the course of the project, I would say the reality has already overtaken our plans. But we set this system now with 4 utility scale PV plus battery systems. On the right-hand side, you see the share of different generation sources, which is not so important for today, but I want to show you is that we look at different load scenarios, noon, evening, and night. With a peak load being close to 200 megawatt. And we look at different scenarios of the system non-synchronous penetration. So the top line, 100% means there is 0 inertia. The second line means 90% SNSP. There is 1 large synchronous machine involved in the system. And the third line is 2 large synchronous machines in the system. The baseline at the bottom is just for comparison. We're not using that for testing. But it's the baseline because that's what the system is today and where we got study results today from HECO. So now looking at the results, what we can see, and now again, my PowerPoint. Give me a second. Yeah, let me just continue while this is still loading. So the biggest challenge, of course, was in this kind of project was to model a system from Hawaii. That's maybe a question that may pop up in your mind. In the past, we used IEEE models. Usually it's difficult to get really dynamic models, RMS models of real systems. Give me a second here. I'm not sure why this is causing so much issue. Stop sharing and then let me maybe reshare. Switching now to PowerPoint, which I hope is a little bit more reliable. Okay. So biggest challenge was the modeling part. We got a PSSE model from HECO that they use today for their planning. We had to do some modifications, of course, to get it up to 100% inverter-based resources and actually to simulate it in a setting where you have no synchronous machines. Those of you familiar with commercial simulation tools know that this is already the first challenge, how to simulate a system when you have no synchronous machine. Some tools, of course, support it, but there are also a good number of tools that's not really support. So what you see here on the slides are the first results. You see here the single line diagram. The island is flipped around, so north is on the right-hand side. You hear different generation units. Overall, when you look at the system, you end up with a system with about 200 states and about 100 controller parameters that we are tuning. And you see here at the bottom an example with initial parameters that have a lot of oscillations, and then the optimized parameters where these oscillations are suppressed significantly. You can see here the frequency, voltage, active and reactive power. So obviously the controller tuning has a huge impact on the dynamics of the system. Now, as I said earlier, we looked at different scenarios, not just one scenario. We have here, as I mentioned earlier, the different load scenarios, noon, evening, and night. We have different scenarios concerning the amount of inertia we have in the system. The first line, 100% as an SP, is without any inertia. The second one is with one large synchronous machine, and the third line is with two large synchronous machines. And then we looked at different contingencies that you can see at the bottom of the screen. So loss of the largest synchronous units, loss of a power line, loss of grid-forming battery inverter, loss of a centralized PV inverter, and loss of 50% of distributed PV inverters. I'm not showing all of them, but you can see here different examples. And in all these examples, you can see on the left figure is before optimization, right-hand side is after dynamic secure pre-optimization. So all these many examples where there is a lot of oscillations before the optimization of the parameters, and then after the optimization, the oscillations are gone. Now, the next step, obviously, this is still offline simulation, and that's what we are working on right now, is bringing this all in the demonstrator and then showing it with the Opal RT real-time simulation, spectrum power energy management system, and then the operator support system on top, which then tells the operator how to tune the parameters or suggests the operator how to tune the parameters in order to make sure the system always stays stable. Now, what I showed you so far was the integration of grid-forming inverters. I showed you the pyramid at the beginning, from grid-forming inverters, from interconnection of grid-forming inverters, now to having different eigenmodes in your system. So the system is oscillating differently. And last but not least, making sure that the lights stay on. That's, of course, still the part we have to show then in the demonstrator, that the protection systems and other systems that may cause a blackout in your system are actually staying safe and closed. But I said all the time, important is to have a scalable solution that goes for a large system. And I can imagine you're wondering, okay, Hawaii is a big island, but of course it's not so big island. So how far can we go? We did some analysis in another project, not in this project, where we wanted to understand how large can we do this optimization. And for Hawaii, it takes about 1 to 2 minutes to optimize, but you can imagine, as I said earlier, if you go to more states, to more controller parameters, the optimization takes longer and longer. So here we did an analysis for a system with about 140 power plants. Again, the problem is, where do you get such a big system? So we took an IEEE 68 bus system that you see on the left-hand side, 9 of them, and just coupled them maybe in a little bit arbitrary fashion, but somehow that we said, okay, this is maybe a system that first is big and then also had some oscillations. As you can see here at the lower left, this is the frequency plot, and you can see there are sustained oscillations in that system. Now, Now you get a system, as I said, almost 150 almost 150 power plants, 2,500 states, almost 1,500 controller parameters that you're tuning. Now, tuning this in one centralized optimization algorithm is quite challenging, but we developed we call it a hierarchical optimization. So there's a central part and there's a distributed part in it. And that's able to solve this problem in some 15 to 20 minutes. It has a nice side effect or an additional feature, which we call information security, increase of information security. And that is that usually in large systems, they are owned and operated by different entities. And of course, in order to do this optimization, you need a very detailed model, but nobody wants to share the detailed model with their neighbor. In this optimization, since it's hierarchical, there is no need actually that one entity has to complete the fully detailed model of the complete system. Yeah, but you are working with abstractions of the detailed models that are exchanged, and it helps both in solving the problem faster, but also in having this information, let's say, sharing only of abstract information and not highly detailed models. So I showed you Hawaii. I showed you the work that we've done to increase or to demonstrate scalability. How can it scale to large systems? Obviously, for this size, we could scale to even larger systems. Question is, does it work in practice? Because so far I only showed you simulations. And we did this actually in one of the very first projects that I was involved in. I mentioned it, Wilpolsried in Bavaria. We had a small part of one feeder disconnected from the main grid and supplying it with 6 parallel grid forming inverters. I mentioned it at the beginning. This was some tests we did before doing this. So here you see the load bank. Eventually, when we were operating the feeder, there was actually a small feeder with real customers, real households in the supermarket and so on. Here, this was a preliminary test that we did in order to understand parallel grid forming of these inverters. These are commercial Siemens Dynamics inverters, but I think the effects that we see would be similar or could be similar with other inverters. And you see here measurements. The first one measurement on the left-hand side is an initial set of parameters where you see 2 inverters, only 2 of the 6 are actually feeding into the load bank, and there is a load step, and then they start oscillating against each other. Obviously, nothing you want to see in your system. We did a manual tuning of the parameters, so we spent quite some time tuning them, and then you see here there's a load step, and here the system is stable, so that would be okay. You can also see the comparison between simulation as dashed line and the measurements as solid lines. So the model is not perfect, but it's reasonably good. Now, what we did afterwards is to really run our optimization on this model, and you can see here 2 examples of the optimization. One where we allow to change also the droop parameters, which of course impacts then on the steady state. And one where we keep the droop parameters constant. And you can see here when you optimize droop parameters, as I said, the steady state, so that the sharing of the load step among the 6 inverters is not equal anymore, but there are hardly any oscillations. And if you fix the droop parameters and only tune the time constants, you can still improve significantly over the manually tuned system. So what you see here is that all these pieces can nicely play together. And now, sorry for this, let me quickly jump back to the slide here. Just giving you a quick summary of my presentation. Everybody here for sure agrees grid forming inverters is a key component of future power systems. It's not something that's coming in 10 or 20 years, but there are actually utilities and TSOs struggling with this already today. I showed you the different layers of complexity we have in order to bring grid forming inverters into, let's say, practically relevant settings like guaranteeing N-1 security. And I showed you also the work that we are doing in our project together with Hawaii, and where we are developing this operator support system. I showed you first results of this, and I'm looking very much forward to your questions in the discussion. Thank you very much.